Hey everyone, welcome to my channel and welcome to one of the first videos in the field of AI that I will publish. Today, I would like to discuss the paper that I don't think got nearly enough attention with the publishing of DeepSeek R1 and Grok 3. This is the paper that was written by Meta researchers and could actually be a pathway to the AGI. The paper is named Training Large Language Models to Reason in Continuous Language Space. For those familiar with the LLMs, I'll briefly go through this abstract so you can understand what's going on here. So what I say is large language models, LLMs, are restricted to reason in the language space, where they typically express the reasoning process with a chain of thought. This is those newer models such as DeepSeek R1. However, we argue that language space might not always be optimal for reasoning. For example, most word tokens are primarily for textual coherence and not essential for reasoning, while some critical tokens require complex planning and pose huge challenges to LLMs. What I claim here essentially is you can imagine if you have a ChatGPT, you can ask ChatGPT simple questions, but you can ask complex math questions, and they'll take similar amount of computation or the exactly same amount of computation for either of those. To explore the potential of LLM reasoning in an restricted latent space instead of using natural language, we introduce a new paradigm, coconut. It's a nice name. Chain of continuous thought. We utilize the last hidden state of the LLM, and this is a major part. Last hidden state of the LLM as a representation of the reasoning state. Rather than decoding this into a word token, we feed it back to the LLM as a subsequent input embedding directly in this continuous space. Experiments show that Coconut can efficiently augment the LLM on several reasoning tasks. This novel latent reasoning paradigm leads to emergent advanced reasoning patterns. The continuous thoughts can encode multiple alternative next reasoning steps, allowing the model to perform a breadth-first search to solve this problem. Why is this important? We'll see later, but essentially, if you think about how LLMs currently are producing words or the next tokens, is they're just going in a straight pathway. They're never exploring multiple options. Rather than prematurely committing into a single deterministic path like COT, Coconut outperforms COT on certain logical reasoning tasks that require substantial backtracking during planning with fewer tokens during inference. These findings demonstrate the promise of latent reasoning and offer valuable insights for future research. So it's a really nice abstract and pretty much sets you for an intro about like what's going to follow in the rest of the paper. So if we continue going down this paper, we can actually see some of the motivations, some of the ideas that are preceding these findings. So if we read further, we can see they say, neuroimaging studies have consistently shown that the language network, a set of brain regions responsible for language comprehension and production, remains largely inactive during various reasoning tasks. Further evidence indicates that the human language is optimized for communication rather than reasoning. And there are actually two pictures down here that we can take a look so you can understand better what's happening. So if you think about a model such as ChatGPT 01, 03, or DeepSeek R1, they're utilizing this chain of thoughts. So for every input token they have some output token, X1, but then this X1 is the next input token. And this goes in the chain. This is why it's called the chain of thoughts. So this would be equivalent to maybe thinking out loud. So imagine someone asks you what's 2 plus 3 times 5. And then you're thinking about loud, okay, 3 times 5 is 15. And then if you take 2 plus, that's 15. Okay, the answer is 17. And this is pretty much how the LLMs in chain of thought are going to work. Chain of continuous thought, Coconut, which is the paradigm developed by Meta, will have a similar paradigm, but instead of the last output being the input to the next, being the next input, what will happen is that the output will never happen. Instead, the hidden layer, so even before outputting, will get feedback to the input, and this will enable some kind of a reasoning because you can pretty much repeat that as many times as you want, and you don't have to output the next token before you're sure that that is the next token. We can see that better defined down here where they define mathematically what's happening. We have this scary formula here, but after all, it's not that scary. You can imagine that every token and every word can be represented as a set of unique numbers or a vector. And in machine learning world, that's called embedding. So you can see that this E of t of all of these E of t pretty much is defined as E of x1 up to E of xt. So there's a bunch of numbers, is a sequence of token embeddings up to the position t. T is pretty much the position of some token that you arrive, up to some position that you arrive. And then this gets fed into the transformer, which is this big neural network that does all of this smart stuff. And then, it comes to the HT, which is the matrix of the last hidden states for all tokens up to position HT. And then this HT can get fed into the softmax. And then softmax pretty much this is the function that will give you probability distribution and will output out the next token. Or instead, what will happen is that this H of t will get fed back into the transformer. And they explain later how is this happening. So let's say the spatial tokens BOT and EOT are employed to mark the beginning and end of the latent thoughts mode respectively. As an example, we assume latent reasoning occurs between the position I and j. Example, x of I is BOT and x of j is EOT, when the model is in the latent mode. So pretty much up, between certain positions, model will be in this thinking mode, and in other positions, token will be, spitting out words. And we use the last hidden state from the previous token to replace the input embedding. And then they show how they replace input embedding. So you can see that, up to x of I, we have original numbers, and then we replace it with the numbers coming from this last hidden state, h of I up to h of t minus 1. And here you can see a nice picture how they're thinking about it. So, between BOT and EOT, they're essentially, having these thoughts, they're thinking, and then once they're done, they pretty much spit the answer out. So here I'm now at this whiteboard, and for those who might not fully understand the LM architecture, I'll try to draw it. So imagine you have an input sequence that is, what is the capital of France? So this can be represented as words. In reality, LLMs are dealing with tokens, but you can imagine token being like a subpart of a word, but for purpose of this exercise, token will be equal to the word. And then, as we said before, each word have its own embedding, which is just a set of numbers. So you can imagine that, for example, word France will be represented as 0.2, minus 0.3, 1, etc. So this could be like a bunch of numbers that represent certain words and they're unique per word. This is called embeddings. And now each of these embeddings, you can imagine that we have like a one big embedding layer that's coming here that will be for like all of these words. So they'll all be connected to this. And then the next layer will be the logic layer, which in the paper they call the transformer. So this is the piece of the network that does all of this cool stuff, calculates attention, and then figures out how should the parameters be set. And then in the next layer, we're gonna have there might be like some additional layers in between such a normalization layer, but the layer that really matters at the end is the final output layer, which one will be used to calculate the probability distribution of each of the words that are possible to come next. So you can imagine that if the question is, what is the capital of France? The answer might be the capital of France is Paris. So there might be a probability for the word D. There might be 30%. The probability for the next word is maybe how, 10%. The probability the next word is a blank space, 10%. So there's like a bunch of probabilities that happen here, and then we take one of these words randomly from this probability distribution and feed it back into the network. And we repeat that for each word. We repeat it for the, and then we go capital, we repeat the same thing. So this is pretty much how it works in the normal LLMs. Like you have a certain word that feeds back into the network, output, and then it goes again. Well, what's the difference in a continuous chain of thought is since it comes from an embedding to this last hidden layer of this transformer that has the main logic of our LLM, instead of going into this output layer and then calculating the probability distribution, it will go directly to the input. And then it will happen once. But imagine you have a more complex query. If you have a query that might be a complicated math query, it will repeat that. And it will repeat that as many times as it needs, or it might be set up as some configuration on the parameter. And once it's finally happy and says, okay, I'm finally happy, I know what the answer should be, Then it will spit the final answer. First, will go here into probability distribution, and then it will spit the final answer here, and then it will start processing the next token. And this is how it's going to go in the sequence. And as you can see from this picture, all of these yellow circles that essentially represent these latent thoughts we talked about. And you can also see that for more complex queries, we won't have constant computation anymore, which will be like one pass through the network for each token, but we might have multiple these circulations until we figure out what the next token is. And this resembles the human brain much better, right? Because in a human brain, if you think about it, essentially, if you have to answer a complex math question, you probably will have to take more time to think about it and answer. If you have to answer some simple trivia question, you might spit out an answer immediately. If we continue further down this paper, we can see how they explain how they've done various experiments on that. So we can see they've tested their model on the math reasoning with the GCM 8K model, but they also tested their model on logical reasoning with the prompt QA model. And this prompt QA model is actually pretty interesting. If you take a look how it looks like, we can see that it's a model that has this long chain of thoughts, nothing to do with the original chain of thoughts, but pretty much like long sentences that go in many different directions, and pretty much like they try to brain tease you in a way. So they might say something like everything that's a numpus or vampus or lorpus is a vampus. Everything that's a grimpus or a dampus or a gorpus is a zampus. Everything that's a grimpus or a dampus or a gorpus is a vampus. So pretty much, they create all of these complicated graph of the thoughts, and then they might ask you, for example, is there any grimpus that is a zampus, for example, and this might even be a bit more complicated for humans to grasp, but it's definitely complicated for language models to grasp. And LLMs currently in existence, such as O1, O3, or DeepSeek R1, will definitely have issues with dealing sets like this. But then if we go into the results they mention, they actually are mentioning this very same thing. So for GCM 8K, which are math problems, chain of thoughts, I think I mentioned where they trained at. They have mentioned that all of these has been trained with a pre-trained GPT-2. So GPT-2 is an early version of a model. It's not a chain of thought model. It's just a normal LLM. But it's pretty good because it's not smart really in a way. So if you use GPT-2 to further train a model with maybe some of your architecture, this might actually enable you to discover new stuff. So this is a fairly complex model, but it's definitely not a model that performs so well. So they used GPT-2 to train this coconut paradigm. And as they trained this coconut paradigm on GPT-2, they tried to do that with chain of thoughts, and for GCM 8K, they achieved accuracy of 42.9%, while for coconut, they achieved 34.1%. So you can see the coconut performs a bit worse than COT on this math set, but if you take a look at the number of spitted out tokens, COT needs 25 tokens to solve the problems on average, while coconut needs only 8.2 tokens. So you can see the tokens does much better. But then if you take a look at this Pronto QA dataset I was talking about before, which is this dataset of all these complicated vampus, lorpus, zampus, vampus, COT, they have a fairly good accuracy on obviously because they've been trained with a chain of thoughts without that room have such a good accuracy, which is 98.8% with a 92.5 tokens. While if you look at the coconut, they have 99.8%, so higher than chain of thoughts with only 9 tokens. This means that coconut is able to essentially, get this representation of all of these complicated sentences in the network, and then, spitting out the tokens that are the answer in much less, output tokens, and they've been able to do that in a higher accuracy. So these are actually pretty interesting results. And then, even if you look at the graph below, we can see, if you take a look at the thoughts per step and accuracy, we can see that the more of these thoughts, these are the circles I was drawing before, like yellow circles, more of these thoughts you're doing per step, higher accuracy you get. So this pretty much means more you think about something, more accurate you get. So these are really interesting results they were able to get with this paradigm. So the answer to this is 540. But what happens here, and what's interesting here, is that you have these hidden states that actually started to resemble some kind of inter-results. So they were able to figure out that, some of the states in between should be maybe 180, 189 with this probability distribution. And they explain this really nicely later. Like the first continuous thought can be decoded into tokens like 180 with a space and 9. So, after the first, thinking thought, which was like in my case, this, yellow circle, one yellow circle, they were able to already figure out some intersteps. Note that the resulting trace for this problem should be 3 times 3 times 6, 60, or is equal 9 times 60, or 540, or 3 times 3 times equals 60, or 3 times 180. So you can see that, it is arriving to the right conclusion slowly over time. It is encoding some of the information, or some of the intersteps in their latent thoughts, which is a really, really interesting finding. Of other findings, this graph is also pretty interesting. All of these like weird words I was telling about before, like a bumpus, vorpus, orpus. You can see, how all of this will be represented in a graph, and essentially, our model has to be able to find all of these paths, and they have to be able to do that, effectively, while pruning other paths. And they have shown that every time they do a new thought, like they have more thoughts, more deep into this graph, they're able to accurately go and prove successfully other paths. This is a bit similar to the Monte Carlo strategy used by AlphaGo, if you're familiar with Google's AlphaGo, and the way they were able to successfully play against human players by pruning different paths. So continuous chain of thoughts or coconut also has to be pruning different paths successfully with the right probability distribution to arrive to the correct answer. So yeah, this is a pretty much very, very interesting findings they had. Yeah, I would just briefly want to jump to the code to see what's happening there. So this piece will be a slightly more technical, but I just quickly wanted to go to code to see how simple it is. So all of this coconut paradigm that I was talking about was implemented in their repo by just 260 lines of code. So it's pretty simple. And the way it works is, you just define this coconut module. They're using PyTorch to implement that. They're defining these embedding layers. Then they are using a forward function to propagate through that. They have input IDs. They have attention mask, which just is used so you can hide training of certain parameters. They use some positional encoding, which doesn't really matter for purpose of this video, and labels. And then you can see that they're doing some custom logic to be able to figure out how many of the continuous chain of thoughts they'll be able to do in a single pass, so for a single token. Then they do some key cache. So these are just optimization stuff, so you can pass stuff to the network faster. And then essentially what they're doing is passing stuff to the network. They get the logits, and then once they're done with all of that, they're using this very important piece here, filling indices. So this will essentially tell you which indices of the embedding that you have in a hidden layer you wanna mark with the new embedding numbers. And then once you have these new embedding numbers, you get this tensor list that gets fed from the input embeddings and embedding numbers, and then essentially you go through all the filling indices, and all these filling indices are getting some token index that goes into the tensor list, and then tensor list gets stacked through the torch back into the input embeddings. So you can see this is pretty much the connection from filling indices to the input embeddings, and this is a for loop. So input embeddings will go back to the beginning of this for loop, and it will continue processing these thoughts as many times as it wants, which depends on this parameter that was extracted here. Once it's ready and done to output, it will go to the final pass. It will go again through this base casual LM. So this base casual LMs exists here as well. This only calls into GPT-2, pretty much calls into GPT-2 to give you certain token back. And then, once it's ready to give the final answer, it will go again here to the output, and it will append to the logit. And then from this logit, it will calculate the cross entropy. This is needed for training purposes. And then at the end, it will return you the output and in terms of the logit. So you can imagine that they're doing probability distribution outside this method. And this is pretty much it, what they're doing. They also have a generate method which generates like a set sequence of tokens. So you can just call directly this method to generate a sequence of tokens, and then they have some other functionality here, which is more on the platform specific. For example, if you're using a sync GPUs. Yeah, this is pretty much all, like the whole piece that they're doing, and and they have all of that into their Facebook research repo. So I deeply recommend anyone who is interested more in that to check it out. For anyone familiar with Python and a bit of PyTorch, this should be fairly simple to follow. And yeah, this will be wrapping up today's video. So I hope it was interesting, and I hope it showed at least partially why this might be a fairly interesting architecture to achieve AGI. And even they mentioned that they detailed analysis highlighted how unconstrained latent space allows model to develop an effective reasoning pattern similar to BFS, but more effective than BFS, and future work is needed to further refine and scale and reasoning models. A promising direction is pre-training LLMs with continuous thoughts, which may enable models to generalize more effectively across the wider range of reasoning scenarios. So this definitely looks like a very promising paper, and definitely looks like something that might be one day developed into a very promised and effective model. This was pretty much it for me today, and yeah, I hope you had fun listening to this video, and hopefully see you next time.